Students, we have been given this question. This is the second lecture in the series of methods of differentiation. So in this class we will be learning about differentiation involving implicit functions, followed by differentiation involving inverse functions, and that would also be followed by deducing identities, and then after the deduction we will perform the differentiation. So these three things would be dealt in this lecture. So we have been given y is equal to 2 raised to the power of log x raised to the power of 2x to the base 2 positive tan pi x over 4 raised to the power of 4 over pi x. We expected to find dy over dx at x is equal to 1. Now whenever the base corresponds to the quantity that is acting as a base for this exponent, we can rewrite this as y is equal to x raised to the power of 2x followed by this quantity, which is tan pi x over 4 raised to the power of 4 over pi x. Now I need to take this quantity as u and this quantity as v, and then I would have to perform the differentiation. Now we are expected to find dy over dx, so this is going to be dy over dx is equal to differentiating u with reference to x, and then followed by differentiating v with reference to x, and finally we will take the point at x is equal to 1. So foremost, what I would do now is, after taking this equation, we would consider u, which is taken to be as x raised to the power of 2x. Now we can take ln both sides. So taking ln both sides, we get this is going to be ln u is equal to ln of x raised to the power of 2x. Now we have a formula, ln a raised to the power of b is equal to b times ln a. So by this formula, this is going to be ln u is equal to 2 times x ln x, and I would be differentiating now with reference to x. So differentiation with reference to x, what do we get? We get 1 over u times du over dx is equal to 2 times of differentiation. This is going to be uv formula, right? X times differentiation of ln x is 1 over x positive ln x times differentiation of x, that's going to be 1. So these two can be cancelled. That would give me 2 times of 1 positive ln x. Now I have a u here, I can push the u, so that u would be over here, so we get du over dx. Now the question is, this has to be found at x is equal to 1. So let me write this in this fashion. U times u is x raised to the power of 2x times 1 positive ln x. This is what I've got. Now taking du over dx at x is equal to 1, this is going to give me 2 times of 1 raised to the power of 2 times of 1 times 1 positive ln 1. Now ln 1 is 0, so I have 2 times 1 times 1. So this is the value that I've got, du over dx at x is equal to 1. So probably we can box this quantity. So having obtained my u, it is I time we also obtain our v. So I will use this base. Consider b being equal to tan pi x over 4 raised to the power of 4 over pi x. Now we take ln on both sides, so I'm going to be stating that taking ln both sides, we get, so this is going to be ln v is equal to ln of tan pi x over 4 raised to the power of 4 over pi x. Since we know this formula, ln of a raised to the power of b is equal to b times ln a, this is equal to 4 over pi times x times ln of tan pi x over 4. So this is what I've got. Now I'm going to rewrite this as 4 over pi times 1 over x times ln of tan pi x over 4, and that's going to be my ln v. Now differentiating with respect to x both sides, we get, so what do we get? This is going to be 1 over v times dv over dx is equal to 4 over pi is a constant, u times v, so that's going to be 1 over x times 1 over tan pi x over 4. Differential of tan is secant squared pi x over 4 times differentiation of pi x over 4, that's going to give me pi over 4. So this is for one particular quantity. Positive differentiation of 1 over x, so this is going to be ln of tan pi x over 4 times differentiation of 1 over x is negative 1 over x squared. So this is what I've got. Now clearly if I were to bring pi over 4, now before bringing pi over 4, let us find out dv over dx at x is equal to 1. Now at x is equal to 1, this is going to be pi over 4. Tan pi over 4 is 1. Ln of 1 will give us 0. So this term goes off. So all we got is 4 over pi, x is equal to 1. That's going to be 1 here. This is going to be pi over 4. So let me place that pi over 4 here times secant squared pi over 4. Now what is that? That's going to be 2. So I got a 2 here. I got, this is x is equal to 1, tan pi over 4 is going to be 1. So this is what I've got. So clearly 4 pi can be cancelled, giving me 2. Of course this v comes over here, right? Now at x is equal to 1, watch here what happens here. At x is equal to 1, this is pi 4 over pi, this is tan pi over 4. Tan pi over 4 is 1. So at x is equal to 1, v is going to be equal to 1. So this can be rewritten as, therefore dv over dx at x is equal to 1 is equal to 2. So I can box this up. So if I were to go back to the original question, so this is equal to 2, this is equal to 2, so this is equal to 4. So I can state therefore dy over dx at x is equal to 1 is equal to 4. So that completes the solution for this beautiful question. Students, we'll move on to the next one. Students, this is a question where we would be using implicit differentiation. So we expected to find dy over dx. So foremost, what I would do is I would start by differentiating both sides with respect to x. So differential of x squared would give me 2 times x. Differential of xy. So we apply uv method. So this is a formula. D of u times v is u times v dash, positive v times u dash. So this is what we would be using here. So x times differential of y is going to be dy over dx. Positive y times differential of x is 1. Positive differential of y cubed is 3 times y squared times dy over dx. Differential of 4 is 0. Now we will collect all the dy over dx terms. So this is going to be 2x positive 2 times x dy over dx. Positive 2 times y positive 3 times y squared dy over dx is equal to 0. So from here dy over dx of 2 times x positive 3 times y squared is equal to, I want to push these two terms on the other side, so it's going to be negative of 2 times x positive 2 times y So I need only dy over dx. So therefore dy over dx is equal to negative. 2 can be taken out. If you want, you can take it out. So x positive y divided by 2 times x positive 3 times y squared. So this is what our dy over dx looks like. Now alternatively, instead of doing all of this, we can simplify the output. In other words, we can obtain dy over dx using this shortcut. So dy over dx is equal to negative dou f over dou x divided by dou f over dou y. So this means differentiating the function with reference to x partially. So when this is happening, you are actually treating y to be as some constant. In this case, differentiating the function with reference to y partially, and in this case when this is occurring, you are taking x to be as some constant. You clearly know differentiating a constant will give us 0. So we have been given this. So I will rewrite this as f is equal to x squared positive 2 times xy positive y cubed negative 4. So this is the way you need to write. So we got a function. So dou f over dou x, this is going to give me 2x. This y is a constant, so I would get 2 times of y because we are differentiating only x. This is going to be 0, this is going to be 0. So now dou f over dou y, this is constant, this is 0, this is treated as constant, so I'll differentiate only y. So if I differentiate only y, I would get 2x here. Differential of 3 times y raised to the power of 3 would give me 3 times y squared. Differential of 4 gives me 0. So therefore I need to start with dy over dx is equal to negative of dou f over dou x. What is that? That's going to be 2 times x positive 2 times y divided by dou f over dou y. What is that? 2 times x positive 3 times y squared. So this is the solution. Now I clearly understand that we have not done any partial differentiation as of now. So this is just for your information, and I wouldn't suggest you all to use this whenever we come across implicit differentiation. So the most appropriate, accepted, or I should say advisable technique is this, and I suggest that you follow this technique. Whereas the other thing is concerned, that is just to keep you informed. So we'll move on to the next question. Students, so we've been given this question: if y is equal to x positive 1 over x positive 1 over x positive 1 over x positive etc., it is a nested expression. We are expected to find dy over dx. Now the question as such looks complicated, but it is easily solvable. The moment that you're able to express this nested expression as some component of y, then the problem becomes easy. Now the catch is to identify which part has to be replaced with y, because y is this infinite nested expression. Now what you need to do is you need to go to this expression and catch that portion alone where you can clearly replace it with y. Now I know that y looks in this fashion, but the same pattern is also observed down the line. Somewhere down the line of this expression you can see the same pattern repeating. Say for example, if I were to close this off, you can clearly see that this is actually the y that has been given in the question. Now since it is an infinite expression, infinite nested expression, we have the liberty of either remove few set of terms or ignore them totally. That's exactly what I'm going to do. What I'm going to do is I'm going to replace this entire set of this infinite nested expression and rewrite it with y. So that is the catch. So this is going to be y is equal to x positive, in place of this entire thing, it's going to be 1 over y. So the moment you are able to write this, the solution becomes simple. So what I'll do is I'll be multiplying by y both sides. So when I do that, I would get y squared here. This is going to be x times y and plus 1. Next is differentiating with respect to x, we get. So the differentiation is both sides, and it is implicit differentiation. So it's going to be 2 times y times dy over dx is equal to u into v. So x times differential of y dy over dx, positive y times differential of 1, differentiating this one would give me 0. So I'm going to bring this dy over dx to the other side. So this is going to be 2 times y dy over dx negative x times dy over dx is equal to y. I can take dy over dx out. That would give me 2 times y negative x is equal to y. I can push this down. If I were to push this down, this is going to give me dy over dx is equal to y over 2 times y negative x. So this is a good place for us to box the result and write the statement ends proved, ends shown, because they want us to show that dy over dx is equal to y over 2y negative x. That's exactly what I have shown here. Students, we are given this question: x times square root of 1 positive y times square root of 1 positive x is equal to 0. We expected to prove 1 positive x raised to the power of 2. So foremost, what I'm going to do is I'm going to consider x times root of 1 positive y times root of 1 positive x is equal to 0. Then I will move this term to the other side. That will give me x times square root of 1 positive y is equal to negative y times square root of 1 positive x. Next I would be squaring both sides. So when I do that, what do we get? This is going to be x squared times 1 positive y is equal to y squared times 1 positive x. The negative sign will vanish because of the fact that we are squaring both sides. So now what we would do is we will remove the parenthesis. In other words, we will distribute the quantities of x squared and y squared, and that would give us x squared positive x squared times y is equal to y squared positive y squared times x. I will move this y squared to the other side, so that would mean I get x squared negative y squared is equal to y squared x. I will move x squared y to this side, so that would mean I get a negative x squared y. Now on the left side, this is of the form a squared negative b squared, so this can be rewritten as x negative y times x positive y. On this end, we can take a x and a y as a common factor. That would give me a y here followed by a x here. Now if I were to take the negative sign out, this is going to give me negative x times y of x negative y. On the left side it's going to be x negative y times x positive y. X negative y can be cancelled, giving me x positive y is equal to negative x into y. I'm going to use this, and I would push this xy to the other side. So that would mean I get x positive y positive x times y is equal to 0. I can take a y out. If I were to do that, this is going to be 1 positive x. There's already an x there, followed by equal to 0. I can move this x on the other side. So if I were to do that, it's going to be y of 1 positive x is equal to negative x, and I can bring this 1 positive x down. So that's going to be negative x over 1 positive x. Now we need to obtain dy over dx. So I'm going to use quotient rule. So d of u over v is equal to v times u dash minus u times v dash divided by v squared. So this is the property that, or I would say the law that we will be using to find dy over dx. So therefore dy over dx is equal to, I'm taking negative sign out, so it's going to be 1 positive x times differential of x, that's going to be 1, followed by a negative sign, x times differential of 1 is 0, differential of x is 1, divided by 1 positive x raised to the power of 2. Now this is going to be equal to negative of 1 times 1, it gives me 1 positive x negative x divided by 1 positive x raised to the power of 2. So clearly positive x negative x gets cancelled, and I get, so when we cancel it off, we get dy over dx is equal to negative 1 over 1 positive x raised to the power of 2, which would convey the result. Hence the result is proved. Students, we have this expression, or I would say we have this equation, y being equal to square root of sin x, positive square root of sin x, positive square root of sin x. It is stretching up to infinity. So this is an expression which is nested in nature. Now, whenever we have nested expressions, we have to make sure that this infinite expression is represented by means of a finite quantity. So when I mean finite quantity is that our objective would be to get rid of this, and the best way to get rid of this is to replace this expression, or in other words, make a connectivity with this expression to the given question. That's exactly what I'm going to do. Now clearly I can see that if I were to block this off, I can see y being present here. That's exactly what I'm going to do. So I'm going to rewrite this as y is equal to square root of, I'm going to retain this first quantity sin x, and then instead of this I'm going to have y. Now our purpose, or I should say our objective, is to find dy over dx. So for that, foremost we need to get rid of this square root. So what I'm going to do is I'm going to be squaring both sides. Now if you were to square both sides, you would get a y squared here, you would get sin x here, and you would get y here. Next I would be differentiating with reference to x, so this is going to give me 2 times y dy over dx. Differential of sin x is going to be cos x, differential of y is dy over dx. Now what I would do is I would push this dy over dx to the other side, so that would give me 2 times y dy over dx, negative dy over dx is equal to cos x. So from here I can write dy over dx of 2 times y negative 1 is equal to cos x, and clearly we can see that therefore dy over dx is equal to cos x over 2 times y negative 1. So this is a good place for us to stop. Students, we are expected to find dy over dx given that y is equal to x raised to the power of x, raised to the power of x, raised to the power of x, and it goes up to infinity. So as I mentioned to you, this is a nested expression, and hence we can block this and see the y being present here. So rewriting, I would now have y to be equal to x raised to the power of y. So now I would differentiate both sides. Of course, before differentiating we will have to take ln both sides. So I'm going to say take ln both sides. So this is going to give me ln y is equal to ln of x raised to the power of y. This can be rewritten as y times ln of x. So now I'm going to differentiate with the reference to x. So this is going to be 1 over y times dy over dx is equal to y times differentiation of x. Ln x is going to give me 1 over x times differential of x is going to be 1, and that is for y, I should say that is for the quantity adjoining y. Positive ln x times differential of y is going to be dy over dx. So now what I'm going to do is I'm going to push this to the other hand. So it's going to be 1 over y dy over dx negative ln of x dy over dx. So this is what I've got, which is equal to y over x. Now I need to get dy over dx. So what I would do is I would extract dy over dx out. That will give me 1 over y negative ln x is equal to y over x. So I've got a beautiful term here. I can take the LCM. So let me just use this space. So I can rewrite this as dy over dx times 1 negative y over ln x divided by y is equal to y over x. So this can be further rewritten as dy over dx is equal to, in fact I can push this down, y over x divided by 1 negative y over ln x divided by y. Now I can flip that y up. So if I flip the y up, this y would move up, right? Because this is like this. Let me write it that. So this is what I've got, because I'm pushing it down and I get this quantity. So if I were to flip it up, this y would go to the numerator. So if it goes to the numerator, that would give me y squared divided by x times of 1 negative y times ln x. So this is my dy over dx. So this is a good place for us to draw the red line, the red box. Students, we are given this question, y raised to the power of 5 positive x times y squared positive x raised to the power of 3 is equal to 4 times x positive 3. We expected to find dy over dx at 2, 3. So foremost we will perform the implicit differentiation. So differentiating with respect to x, we get, so what do we get? Differential of y raised to the power of 5 is 5 times y raised to the power of 4 times dy over dx positive, this is uv formula. So x times 2 times y times dy over dx positive y squared into differentiation of x is 1. Positive differentiation of x cubed is 3 times x squared is equal to differentiation of 4 times x is 4. Differentiation of 3 would give me 0. So I can extract dy over dx out. So this would give me 5 times y raised to the power of 4 positive 2 times xy positive y squared positive 3 times x squared is equal to 4. Now I need to extract the value of dy over dx at 2 and 1. So x is 2 and y is 1. So we can simply substitute the value. So this is going to be dy over dx of 5 times of y is 1. So it's going to be 1 there. Positive x is 2. 2 times 2 is 4. Y is 1. So this is what I get. Positive 1 positive 4. 4 times 3 is 12 is equal to 4. This is going to be giving me dy over dx of 5 positive 4 is 9 positive 13. I can push the 13 to the other side. So that's going to be 4 negative 13. 4 negative 13 would give me negative 9. And I already have dy over dx with a 9. I can push the 9 down. So this would mean these two things would get cancelled. Therefore I get dy over dx is equal to negative 1. So this is the value that we have got. Now alternatively, you can also do the same question in this following fashion. So let me just show that also, in case if time is a big constraint for you. So I'm going to obtain dy over dx to be equal to negative df over dx dou, it's actually dou f over dou x divided by dou f over dou y. So partial differentiation. So for that, what we need to do is, let me use this space over here. So I'm going to rewrite this as f is equal to y raised to the power of 5 positive x times y squared positive x raised to the power of 3 negative 4x negative 3. So this is my function. So I start off with differentiating the function with reference to x partially. So it's a partial differentiation. That means y is constant. So we start off with differentiating y raised to the power of 5, which is 0. This differentiation would give me y squared. This differentiation would give me 3 times x squared. This differentiation would give me negative 4. This differentiation would give me 0. Now differentiating with reference to y, this is going to be 5 times y raised to the power of 4 positive 2 times x times y and this is 0, this is 0. So this is what we've got. So at x is equal to 2 and y is equal to 1, so what happens? This is equal to negative of, this is 1, 2 squared 4, 4 times 3 12, negative 4 divided by 5, 2 times 2 4, 4 times 1, that's 4 there. So 13 negative 4, that's going to give me 9, and 9 here, 9 gets cancelled, giving me negative 1. So two different ways, and they get us the same solution. So you can see that negative 1 is a solution here, negative 1 is a solution here. Students were given this question: if x raised to the power of y is equal to e raised to the power of x negative y, we expected to prove that dy over dx is equal to ln x divided by 1 positive ln x raised to the power of 2. So in this case, let us start off by stating this: consider x raised to the power of y is equal to e raised to the power of x negative y. Now I would be taking ln both sides, we get. So this is going to be ln of x raised to the power of y is equal to ln of e raised to the power of x negative y. Now this is to the base e, so clearly I can rewrite this as x negative y. Now there is a formula: ln of a raised to the power of b is equal to b times ln a. Now because of this formula, I can rewrite this as y times ln x. Now I would be differentiating both sides with respect to x. So when we do that, we get, this is going to be y times differential of ln x is 1 over x times differential of x is 1, positive ln x times differential of y is dy over dx. This is equal to differentiation of x is 1, differentiation of y is dy over dx. Now what I'm going to do is I'm going to move this dy over dx to this side. So I get dy over dx ln x positive dy over dx is equal to, I have a 1 here, and y times 1 over x, so I can push that. So this is what I've got. Now let me use this part of the space. So from here I am going to take dy over dx out, so that would give me ln x positive 1 is equal to 1 negative y over x. So therefore dy over dx is equal to 1 negative y over x divided by, I'm going to write this as 1 positive ln x. Now if you see the question, we do not have y over x, so we just have ln x, so we need to get rid of this. How are we going to get rid of this? By considering, now consider, I'm going to be considering the system. So this is what I'm going to consider. So consider 2. So now consider 2. So what we got? We got y times ln of x is equal to x negative y. Now I will divide by x. So if I were to divide by x both sides, so if you divide by x both sides, this is going to be y over x times ln x is equal to x over x negative y over x. This can be cancelled. So this is going to give me 1 negative y over x and y over x times ln x. I know you would be tempted to use 1 negative y over x over here, but don't do that, because still we have got y over x. We need to get rid of that. So how are we going to get rid of that? Just push this to the other side. So you get y over x times ln x, positive y over x is equal to 1. If I were to take y over x out, I would get ln x positive 1 is equal to 1. So this is a beautiful expression I've got. Now from here I can rewrite y over x is equal to 1 over ln x positive 1. So this is a very good representation for y over x. So what I would now do is I would take this as 3. right? Now consider 3. So what is 3? dy over dx is equal to 1 negative y over x divided by 1 positive ln x. Now since y over x is equal to 1 over 1 plus ln x, I'm just writing it as 1 plus ln x. So if I were to take this as say sum 4 or sum 5, maybe I can retain or represent this by 4, but it doesn't matter. So therefore 5 can be rewritten as dy over dx is equal to 1 negative 1 over 1 plus ln x divided by 1 plus ln x. So if I were to take the LCM, this is going to give me 1 plus ln x negative 1 divided by 1 plus ln x divided by 1 plus ln x. So I can push this to the denominator. In fact, this is actually 1 plus ln x over 1. So when you flip it, the 1 goes to the numerator, 1 plus ln x remains in the denominator. So positive 1, negative 1 gets cancelled, giving me ln x over 1 plus ln x times 1 plus ln x, which is equal to ln x over 1 plus ln x raised to the power of 2, which is my dy over dx. So this is an amazing question for the fact that we need to bring this result in this fashion, ln x over 1 plus ln x raised to the power of 2. So we'll move on to the next question, students. Now we will start our study on derivatives of inverse functions. Now if g is the inverse of f of x, then we can write this expression, this statement as g of f of x is equal to x, for the fact that g is the inverse of the function. Now if I were to differentiate both sides with respect to x, then I would get g dash of f of x times differentiation of f of x, that's f dash of x, times differentiation of x, that's going to be 1. On the right hand side I get 1 here. Now I can rewrite this as, let me use this space over here. So from here I can rewrite this entire equation as g dash of f of x is equal to 1 over f dash of x, and this is exactly the formula we will be using. So this is very important. So g dash of f of x is equal to 1 over f dash of x. So having obtained this all important relationship that connects the derivative of the inverse of a function to the derivative of a function, we will be using this to solve related questions. Students, we are given this question: if f of x is equal to x raised to the power of 3 positive x raised to the power of 5 and g is the inverse of f, find g dash of 2. Now we know that I'm going to use the formula which I've just shown you in the previous discussion. So g dash of f of x is equal to 1 over f dash of x. We know this. So I'm exactly going to be using this. Now given, what is given? F of x is equal to x raised to the power of 3 positive x raised to the power of 5. Now at x is equal to 1, we get f of 1 is equal to 1 positive 1 is equal to 2. So if I were to take this as 1, therefore 1 can be rewritten as g dash of, in place of f of x, we need to use this value because we are expected to find g dash of 2. So f of 1, that's going to be 2, is equal to 1 over f dash of x being equal to 1. So differentiating with respect to x, we get, so f dash of x is equal to 3 times x squared positive 5 times x to the power of 4. At x is equal to 1, what happens? At x is equal to 1, this is going to be 3 positive 5 is equal to 8. So if I were to take this as 2, hence 2 becomes g dash of 2 is equal to 1 over f dash at x is equal to 1 is equal to 8. So this is a good place for us to draw the red line. Now we were able to get this value mainly because of this all important formula which we have achieved. So we will move on to the next question. Students, we are given this question: if f of x is equal to exp of x cubed positive x squared positive x for any real x and g be the inverse of f, we are expected to find g dash of e raised to the power of 3. So to solve this question, foremost we will use the relationship that connects g dash and f dash. So we know that g dash of f of x is equal to 1 over f dash of x. So this is the all important relationship that is needed to solve this question. Now given, what is given? F of x is equal to, now exp of x cubed positive x squared positive x can be written as e raised to the power of x cubed positive x squared positive x. So we are expected to find e raised to the power of 3. So we need to have a 3 there. So for that we need to get the value of the function at x is equal to 1. So this means f of 1 is equal to e raised to the power of 1 positive 1 positive 1, which is equal to e raised to the power of 3. So hence if I were to take this as 2, therefore 2 can be rewritten as g dash of e raised to the power of 3 is equal to 1 over f dash of x is equal to 1. So this is what we have to get. Now consider f of x, which is equal to e raised to the power of x cubed positive x squared positive x. Now differentiating with respect to x, we get f dash of x, this is nothing but x, so just visualize it like that. So this is going to be e raised to the power of x cubed positive x squared positive x times differentiation of this entire quantity, that's going to be 3x squared positive 2x positive 1. So at x is equal to 1, that's required. So at x is equal to 1, you get f dash of 1 is equal to e raised to the power of 1 positive 1 positive 1 times 3 of 1 squared positive 2 of 1 positive 1. So this is going to be e raised to the power of 3. This is 3 positive 2 positive 1. 3 positive 2, 5, 5 positive 1 is 6. This is going to be 6 times e raised to the power of 3, which is equal to f dash of 1. So we have got this. Now all you need to do is go over here. So if I were to take this as 3, so therefore 3 can be rewritten as g dash of e raised to the power of 3 is equal to 1 over f dash of 1 is 6 times e raised to the power of 3. So that is what we have got, and it is a good place for us to draw the red line. Students, we are given this question: if g is the inverse of f and f dash of x is 1 over 1 positive x raised to the power of n, we are expected to prove that g dash of x is equal to 1 positive g raised to the power of n of x. Now we know that the all important relationship between g dash and f dash, so that is g dash of f of x is equal to 1 over f dash of x, but f dash of x is given to be as 1 over 1 positive x raised to the power of n. So if I were to flip it, this is going to be 1 positive x raised to the power of n. So now we have got g dash to be as f of x is equal to 1 positive x raised to the power of n. Now we need to make certain substitutions so that we can have an x here. Now how is it possible to have an x? If we can take, let x be equal to g of x. Please remember, g is the inverse of f. So if I were to take x is equal to g of x, so this would mean f of g of x will be equal to x. So this is for your understanding. So I'm going to take x is equal to g of x. So if I were to take x is equal to g of x, this is going to be, let me write that down, g dash of f of x. So f of, instead of x, is going to be g of x, and this is equal to 1 positive, x is g of x. So g of x, that's raised to the power of n, so I can write it as g raised to the power of n, like this. Now f of g of x, what is that? That's nothing but x. So this is going to be g dash of x is equal to 1 positive g raised to the power of n times x. And what is that? This is exactly what we are looking for. So we can box this and say hence proved. Hence proved. So that completes this question. We'll move on to the next one. Students, we are given a beautiful question. If cos x over 2 times cos x over 2 squared times cos x over 2 cubed, etc., up unto cos x over 2 raised to the power of n is equal to sin x. This is given. We expected to prove that sigma r is equal to 1 to n of 1 over 2 raised to the power of r times tan x over 2 raised to the power of r is equal to 1 over 2 raised to the power of n times cot x raised to the power of 2 raised to the power of n negative cot x. So this is a nice question to challenge the intellectual bliss of the mind. So having got this question, let us approach this question by using logs. So what I will do is I will start off by stating, consider the given question, which is cos x over 2 times cos x over 2 squared times cos x over 2 raised to the power of 3, etc. Cos x over 2 raised to the power of n is equal to sin x over 2 raised to the power of n times sin of x over 2 raised to the power of n. Now, taking ln both sides, we get, so what do we get when we do that? So this is going to be ln of this entire quantity is equal to ln of sin x over 2 raised to the power of n times sin of x over 2 raised to the power of n. So this is what we got. Now ln AB is equal to ln A plus ln B, and ln of A over B is ln A negative ln B. I would be using this property over here and this property over here. So this would give me ln of cos x over 2 positive ln cos x over 2 squared positive ln cos x over 2 cubed, etc. positive ln cos x over 2 raised to the power of n is equal to ln of sin x negative ln of 2 raised to the power of n times sin of x over 2 raised to the power of n. Now let me simplify the right hand side. So this is ln of sine x, ln AB. So this is going to be ln 2 raised to the power of n negative ln sine of x over 2 raised to the power of n. Because of the negative sign, it would be hitting all these terms. Now on the left side, let me rewrite that. Ln cos x over 2 positive ln cos x over 2 squared positive ln cos x over 2 cubed plus etc. plus ln cos x over 2 raised to the power of n. This is what we've got. So differentiating with respect to x, we get, so differentiation of this is going to be 1 over cos of x over 2 times differentiation of cos, that's negative sine over x over 2 times differentiation of x over 2, that's going to be 1 over 2. So this is what we have got. So if I were to rewrite this, I would have to rewrite it in this fashion. So let me just show you that. So this is equal to negative 1 over 2 sine of x over 2 divided by cos of x over 2. So this is how we would be rewriting it. So I will follow the same thing. So this is going to be plus 1 over, I'll write it like this, 1 over cos x over 2 squared times differentiation of cos, that's going to be sine of x over 2 squared with a negative sign times differentiation of x over 2 squared, that's going to be 1 over 2 squared. So this is what we have got. So the next thing is plus, same thing, I'm going to repeat it, 1 over 2 cubed times sine of x over 2 cubed divided by cos of x over 2 cubed plus etc. This one is going to be negative 1 over 2 raised to the power of n times sine of x over 2 raised to the power of n times cos of x over 2 raised to the power of n. So this is what I've got for this left hand side, is equal to right hand side 1 over sine x times the differential of sine x is cos x, differentiation of x is 1, this would vanish, followed by negative 1 over sine of x over 2 raised to the power of n times differentiation of sine x, that's going to be cos. So I'm going to write it over here. So cos of x over 2 raised to the power of n times 1 over 2 raised to the power of n. So this is what I would get. So now I got a negative sign, negative sign, negative sign, negative sign. So I'm going to take that negative sign out. So if I were to take that negative sign out, this is going to give me 1 over 2 times tan of x over 2 plus 1 over 2 squared tan of x over 2 squared plus 1 over 2 cubed tan of x over 2 cubed plus etc. 1 over 2 raised to the power of n tan of x over 2 raised to the power of n. Right. Now on this side, this cos over sine, that's cot x, and negative 1 over 2 power n. So this is cot x over 2 raised to the power of n. Now I can push this negative sign onto the right side. So that would mean I would now have 1 over 2 raised to the power of n cot x over 2 raised to the power of n negative cot x, and on the left hand side this is going to be 1 over 2 tan x over 2 positive 1 over 2 squared tan x over 2 squared positive 1 over 2 cubed tan x over 2 cubed plus etc. 1 over 2 raised to the power of n tan x over 2 raised to the power of n. This is what I have got. Now this can be rewritten with the series expansion. sigma r is equal to 1 to n 1 over 2 raised to the power of r. When r is equal to 1, this is 1 over 2 times tan x over 2 raised to the power of r. So clearly I get the first term when r is equal to 1, right? 1 over 2 times tan x over 2 raised to the power of 1. The first term when r is equal to 2, the second term r is equal to 3, the third term, and so on and so forth, which is equal to, on the right side I get 1 over 2 raised to the power of n times cot x over 2 raised to the power of n negative cot x. So what is this? This is exactly what we are required to show, right? So we can state that n's proved, and that's a good place for us to draw the red line. Students, we are given this question: if 1 positive x raised to the power of n is equal to c0 positive c1x positive c2x squared and goes on up unto cn x raised to the power of n, we are expected to show that c1, this expansion is equal to n times 2 raised to the power of n minus 1. So we need to prove this. This is required. So what I am going to do is, I'm just going to start off by consider 1 positive x raised to the power of n is equal to c0 plus c1 times x plus c2 times x squared plus etc. cn x raised to the power of n. So what I will do is I will be differentiating with respect to x both sides. So when we do that, this is going to be n times 1 positive x raised to the power of n negative 1. Differential of c0 is c0 is 0. Differential of c1x gives me c1. This is going to give me 2 times c2 times x, and the next term would be giving me that's going to be c3, right? c3x to the power of 3. So it's going to be 3 times c3 x to the power of 2 plus etc. The last term, this term is going to give me n times cn x raised to the power of n negative 1. So this is what we have got. Now we are expected to change this to this, and that would mean the proof is complete. How are we going to do that? Now to achieve the result, we are going to take, let x be equal to 1. If I were to take x be equal to 1, this is going to give me n times 1 positive 1 raised to the power of n negative 1 is equal to c1 plus 2 times c2 plus 3 times c3 plus etc. n times cn times x is equal to 1. So 1 raised to the power of n minus 1, that's going to give me 1. Now go to the left hand side. What do you get? 1 added with 1, that's going to give me 2. So I get n times 2 raised to the power of n minus 1 is equal to c1 plus 2 times c2 plus 3 times c3 plus etc. n times cn. So what is that? Just go and compare. This is exactly the term that we have got, and this is exactly the term that we have got. So the conclusion is n's proved. So that's a good place for us to draw the red line and move on to the next question. If in case we are expected to also prove this, say c0 positive, 2 times c1 positive, 3 times c2 etc. up unto n positive 1 times cn is equal to n positive 2 times 2 raised to the power of n negative 1, then we can also achieve this result. So what are we given? We are given that 1 positive x raised to the power of n is equal to c0 positive c1x positive c times, in fact it's positive c2 times x squared positive c3 times x to the power of 3 plus etc. And this is cn x raised to the power of n. This is what has been provided for us. Now I will be multiplying left side and right side by x, so that would mean I now have x times of 1 positive x raised to the power of n is equal to c0 x positive c1 x squared, positive c2 x to the power of 3, positive c3 x to the power of 4, plus etc. Cn, x is being multiplied, so this is going to be x positive, x raised to the power of n positive 1. So that is fine. Now let us differentiate the quantity with respect to x we get. So what do we get? This is u into v form, so it's going to be x times differentiation of 1 positive x raised to the power of n. That's going to be 1 times 1 positive x raised to the power of n. We are actually removing 1, so n negative 1 positive. Differentiation of x would give me 1, so it's going to be 1 positive x raised to the power of n. This is going to give me c0 plus 2 times c1x plus 3 times c2 x to the power of 2, and plus so on and so forth. This is going to give me n positive 1 times cn x raised to the power of n positive 1 minus 1, so that's going to be x raised to the power of n there. Now the question now comes, what happens if I take x to be equal to 1? If I were to take x to be equal to 1, this is going to give me c0 plus 2 times c1 plus 3 times c2. See that? 3 times c2, 3 times c2, that's fine. Plus etc. n positive 1 cn, 1 raised to the power of n, that's going to be 1. So the quantity that we have here represents this quantity which is expected to be proved. So one side is already completed. We need to show this side. We need to get this side. So x is equal to 1. This is going to be 1 of n of 1 positive 1 raised to the power of n negative 1 positive 1 positive 1 raised to the power of n. So this is going to be 1 positive 1 is 2 raised to the power of n. So it's going to be n times 2 raised to the power of n negative 1 positive 2 raised to the power of n is equal to c0 plus 2 times c1 plus 3 times c2 plus etc. plus n positive 1 times cn. Now what I wish to do is I need to get this n positive 2. So to get that n positive 2, I want to, if I were to take say 2 raised to the power of n minus, if I were to take this out, so let's see what we are getting. So if I were to take 2 raised to the power of n minus 1 out, I would get an n here. Now I need to get 2 raised to the power of n here. So that has to be added with a 2, because 2 raised to the power of n times 2 would give me 2 raised to the power of n, right? So 2 raised to the power of n minus 1, when we multiply it with 2, obviously gives us this value. So it's straightforward. So this is equal to c0 plus 2 times c1 plus 3 times c2 plus etc. plus n positive 1 times cn. So clearly we can see that the quantity that we have achieved here is the same as the quantity that is expected. So clearly we can now conclude, hence the result is proved. And this is a good place for us to draw the red line. Thank you, students. With this we complete this class's lecture for this topic, and we will move on to the next topic.